All right, guys, welcome to the last unit in AP Chemistry, first of all. So congratulations for getting this far. And in this unit, we're going to look at electrochemistry. Now, I'll be upfront with you. Electrochemistry is a branch all of its own. So you could spend a tremendous amount of time studying this subject and still only be an amateur at it. As far as AP is concerned, we're going to look at a couple very specific portions of electrochemistry. We're going to look at redox, we're going to look at voltaic cells, we're going to look at batteries, but we're really just going to scratch the surface of it. So electrochemistry is really important in things like engineering, in things like battery production, solar power. Lots of different fields can apply electrochemistry to, or a lot of different fields have electrochemistry as part of the application of their field. So if this kind of stuff interests you, there are plenty of careers down the road that you could use a little bit of electrochemistry in. So it's a pretty interesting subject. Let's jump in. Electrochemistry is just the study of the relationships between electricity and chemical reactions. We're going to look at primarily spontaneous reactions like our voltaic cells, but it also covers some non-spontaneous processes as well. Now, as a reminder, we're going to start with redox chemistry. If you don't remember how to assign a redox number to an element in a compound, or an element by itself for that matter in a reaction, this is just a brief review of those rules from last year. So a pure element would be 0. A monatomic ion, whatever its charge is the charge, or is rather the oxidation number. Fluorine's -1, oxygen's -2 unless it's peroxide, in which case it's -1. H is going to be +1 unless it's part of a hydride, where it will be -1. Remember that the sum of the oxidation numbers has to equal the overall charge of the species. 0 if it's a neutral compound, whatever the charge is if it's an ion. Okay, so those are just a simple recap of the rules. Now, what oxidation numbers allow us to do is kind of some bookkeeping. Remember, the oxidation number is not the actual charge, it's just the apparent charge at that moment. So when you're looking at oxidation numbers on the reactant side compared to the product side, then if the oxidation number is going to increase, then that element has been oxidized. If the oxidation number decreases, that element has been reduced. We can remember that with the phrase oil rig. Right? Oxidation is loss of electrons, reduction is gain of electrons. And again, we're talking about the reduction in charge, which happens when you gain negative electrons. Right? Now here you can see an example of a redox reaction. We have zinc and hydrogen. Zinc has gone from 0 because it's a pure element. Its oxidation state is 0 to +2. Hydrogen has gone from +1 as an ion to 0 as a diatomic molecule. So we can look at the charge and say, all right, well, zinc went from 0 to +2, so it was oxidized. Hydrogen went from 1 to 0, so it went down the number line, so it was reduced. The oxidizing agent is something that causes something else to be oxidized. In this case, that would be the hydrogen. The reducing agent causes something to be reduced, in this case, the zinc. Right? The zinc led to the reduction of hydrogen. That's what we're seeing there. Now, where this can start to get complicated is when it's time to balance the reactions that are involved in oxidation reduction. And a lot of times what we do in order to kind of simplify this is to balance them in terms of a half reaction. So if we look at tin and iron, when they react, you break them into the oxidation half reaction, which we have first here, and the reduction half reaction, which we have second. And you can see that with this has already been balanced. The 2's have been added for iron. But beforehand, it would have been iron +3 plus 1 electron gives us iron +2. The problem is when we look at tin, we see it's going from 2+ to 4+, which means it has produced 2 electrons. So the initial writing of this would look like that. We would see we have an issue here. We have 1 electron on the bottom compared to 2 on the top. And so if we balance the reaction using the half reactions and we balance out our electrons, that is one way that we can solve that problem. So in order to look at that, here are the rules for balancing a redox equation with the half reaction method. So there's 4 basic steps. We want to balance all the atoms other than O and H. We want to balance oxygens by adding waters. We want to balance hydrogens by adding H pluses. And then finally, we want to balance our electrons. In order to do this, we follow these 7 steps here on the left. We make our 2 half reactions, 1 oxidation, 1 reduction. We're going to balance all of the atoms other than O and H, right? Then do O and H. Add electrons to figure out your charges. If we need to, we can multiply by some common factors to make our electrons in both half reactions equal. Add the 2 reactions up, just like we did like with the Hess's law problem, and then we can simplify that out if we need to. The last thing you always want to do is count your atoms. Make sure that you've actually balanced it. Let's do one of those. So this is a reaction between permanganate, which is the MnO4 minus species there, and oxalate, which is the C2O4 minus species. So when we react those 2 things together, this is what we get. We get manganese 2 plus and we get carbon dioxide. If we put oxidation numbers in here, we can see that the manganese is being reduced. So on this side, we have -2, and so we have something, Mn, plus a -8. It's going to equal -1. All right, so that must be +7. So the manganese number here is +7. For carbon, we have 2 carbons plus -8, right, is going to equal -2. And when we solve that out, we're going to get +3, -2 there. All right. And then on the right, well, we have an ion by itself, so we've just got +2. That's the oxidation state. This is going to be -2, so blank -4 equals 0, so this must be +4. So we can see that carbon has changed. It's increased. And we can see that manganese has been reduced. So manganese went from +7 to +2. Carbon was oxidized. It went from +3 to +4. How can we balance this out then? Well, start with the oxidation half reaction. First thing we need to do is balance the carbon, right? We leave O and H to the end. We leave the charge to the end. So I need to add a 2. Put a 2 in front of carbon dioxide. My carbons are good. Subsequently, also the oxygens are good. To balance the charges, we have to add some electrons. We need them on the right side. These electrons had to go somewhere, those 2 negative electrons, and so we put them right there. So that has now balanced our oxidation side. When we do our reduction half reaction, MnO4 minus is becoming Mn2 plus, and so our manganese number is fine, but now we got to have oxygen. So remember, we balance oxygen by adding waters. We have 4 oxygens on the left, so we need 4 waters on the right. Whatever that number is for oxygen, that's how many waters we're going to add. But now we've created a problem, right? We've introduced hydrogen, and there's no hydrogen here on the left. So in order to get rid of that, we add H plus, right? To get rid of hydrogen, the rule says add H plus to the other side. In this case, we need 8 of them because 2 times 4 gives me 8 hydrogens. So 8 hydrogens on the left. So I add those. Now all of our elements are good. Now we need to figure out how to balance our charges. So in order to balance the charge, we need to add 5 electrons to the left side. That's going to give us a net of 2 plus on the right side. All right, hopefully everybody can see that there. Now, when we put those 2 things together, all right, we need to make sure the electrons are equal on both sides. And the problem is we've got 2 here and we've got 5 there. Well, 2 and 5 don't really have a number in common, so we just do times 5 up top and times 2 at the bottom. That's what we're going to do. That's going to give us changes everything, right? We're going to change all of our coefficients when we multiply, not just the electrons. When we add those together, we get this ginormous reaction right here. And on that reaction, the only thing that appears in common on both sides are the electrons. And that's a good thing. That's what's supposed to happen. So now we can get rid of them. We just cross them out. They appear on the left and the right. It's the similar concept to spectator ions. All right. And so we're just going to get rid of them. And now we have our balanced reaction. So even though we weren't aware of the fact that the H plus, the acid in this case, was involved, we have shown that that is the case because we've balanced this by using our half reaction method. So this is the final balanced equation that we want. And that's great for an acid, but just as a side note, you can also balance in a basic solution. All right, so if something happens in a basic solution, we're going to treat it just like it occurs in acid. And once everything is balanced, you're going to add hydroxides to both sides to neutralize the H in the equation. So like on the left side, right, this is going to produce water. And on the right side, it should produce some water. And when you subtract it out, you're going to have more water on one side than the other. And so probably on the product side, we're going to have the creation of some water there. So not really anything crazy, just we can do it in an acidic solution. In an acidic solution, we can also do it in a basic solution, and the rule still applies. All right, so that's all the redox stuff. Now let's talk about the application of this information. So a voltaic cell is a way to take the spontaneous reaction that occurs when things, reduce or oxidize, and transfer that into some kind of usable electrical work. Now, if you set your cell up correctly, if you set your experiment up correctly, you'll know where the electrons are going to flow. And if instead of running them through a voltmeter here, we run them through something like a generator, we can actually turn a motor or whatever we want to do. In order to set one of these voltaic cells up, we just have to make sure that the two reactants are not in contact with each other. So all of the oxidation is going to occur on the anode side. All of the reduction is going to occur at the cathode side. Now, in order to make sure the electrons can flow from place to place, we hook a wire to the anode and the cathode. A lot of times we'll put a switch in here so that we can cut it on or off as we need to. And we'll also have a voltmeter there that will register, how much electricity is coming out there, how many volts. The other thing that we have to do is have this salt bridge. And a salt bridge is, I think on the next slide. No. So, no, it's on the slide. There it is. A salt bridge usually has some kind of electrolytic solution in a gel. And the reason it's in a gel is because if you just have it in a solution, when you turn your U-shaped tube upside down, then it all runs out. So you need to keep it in a gel. And the gel is going to allow those ions to migrate back and forth. And it's what closes the circuit. So the electrons are flowing up here. They're flowing from the anode to the cathode. The ions are flowing through the salt bridge. All right, so some salt is going to go, or some of the anions are going to go left towards the anode. So all of the anions migrate towards the anode. Any of the cations are going to migrate towards the cathode. Now, there's a lot of different ways you can set it up. You can see it here. They have this porous glass disc, which allows things to move back, the ions to move back and forth. You can set it up with a salt bridge. You can set it up with a, glass disc. If you're making a battery, which we'll talk about in the second video, batteries sometimes use porous fabric. Whatever it is that you use, it just has to allow ions to move back and forth through the solution. That's what's going to close your circuit, and that's what's going to allow your electrons to flow. Now, when you have this voltaic cell, it's important to know, number one, electrons are going to leave the anode, and they're going to flow through the wire to the cathode. All of the cations are going to be formed in your anode compartment. Wow, these words are killing me today. And as the electrons get to your cathode, the cations are going to be attracted to that negative cathode, which is going to get them deposited as a metal on that cathode. Okay, so you have a lot of different things that are occurring in this cell. Take some time to look at the pictures in this chapter and understand them, because the pictures are really good in chapter 20. Okay, so look over those. And I've included some of them here, but there are some more, and the descriptions of those will help you understand what the movement is that's going on. Basically, what we want to make sure we have down pat in this video is two things. Number one, the electrons are flowing from the anode to the cathode through the wire, through the connection of the anode to the cathode. The cations and the anions are flowing through the solution, either through the porous membrane, which is in this picture, or through the salt bridge, either one. Cations are flowing from the anode compartment where they're made, to the cathode compartment where they are deposited. Anions are made in the cathode compartment and are flowing to the anode where they're going to be deposited. You could also have this with a salt bridge, right, which would look something like that. Okay? We call both sides of this a half cell. Right, so that's something that we'll see. Now, a half cell is great and all that stuff, all that setup is good, but we have to be able to quantify the capabilities of a cell. And in order to do that, we talk about something called EMF, which is the electromotive force. This is comparable to basically a waterfall, right? So electrons are going to flow spontaneously from high potential to low potential. And an anode has higher potential energy than a cathode. So the electrons, you don't have to do anything. The electrons just leave the anode and flow to the cathode. That's what they do. If they happen to go through something, in some invention we have along the way, they can do some work. And that's basically what a battery does, or what our electrical power allows us to do. Now, an EMF, electromotive force, and potential difference all mean the same thing. So if you hear someone say cell potential, or E sub cell, or potential difference, or electromotive force, all of those things are used interchangeably. Now, the E of the cell, the electromotive force of the cell, all right, is measured in volts. All right, a volt is 1 joule per coulomb. The coulomb is, let me check my notes here because I wrote it down because I wanted you to have it because it's not in your book. Here we go. A coulomb, so 1 C, right, is the SI unit of electrical charge, okay? And it is the quantity of electricity conveyed in 1 second, right, by a current of 1 amp. Okay, that's a coulomb. And if you're wondering what an amp is 1 coulomb of electric charge. And that is 6.24 times 10 to the 18th charge carriers. Okay, charge carriers are typically electrons. So that's 1 coulomb. 1 amp. All right. There's 1 coulomb of these charged characters. When we measure our volts, remember volts are in joules per coulomb. One other thing that comes from this that's fairly important is that we need to know what an electron is. So 1 electron, just by itself, is 1.6 times 10 to the negative 19th coulombs. All right, so there we go. Lots of different things to write down to have just in case you need to reference them. Once we have a cell set up and we want to look at this E sub cell, all right, the reduction potential, or the EMF of a cell, we want to calculate that. And one of the ways that we calculate it is, slide right here, we look at the standard electric potential, or the standard EMF of the cell, and we look at that in terms of the cathode compared to the anode. Now, we tabulate these things, and we always tabulate them in terms of how they are reducing, like reduction. And we base them on the defined zero, which is the reduction of hydrogen to hydrogen ion to hydrogen gas. Now, this is called the She, which is the standard hydrogen electrode, or the Her, the hydrogen electrode reference, or the NHE, which is the normal hydrogen electrode. I've heard all different kinds there. But by definition, its reduction potential is always 0 volts. So we just compare what everything is compared to hydrogen. We set hydrogen as an arbitrary 0. Once we can do that, we can tabulate, right, the cathode minus the anode to give us the cells, like whatever cell you're setting up, whatever's on the anode, whatever on the cathode side, we can figure out its electropotential. Now, it's really important that you understand that this is an intensive property. It doesn't matter what you do concentration-wise, the reduction potential is going to stay the same. It just may go up in number of the amount of energy or the charge that's produced, but the ratio is going to remain the same. I do have a secondary video I'm going to make with some sample problems. We're going to look at this a little bit closer. Now, here is one from your textbook, which is a pretty good example. It goes back to that one we looked at earlier. The reduction potential for this cell, for the cell on the left, the zinc cell, all right, that's our anode, is negative 0.76 volts. For the cathode, it's plus 0.34 volts. So for the total cell under standard conditions, so 1 atmosphere, 298 Kelvin, 1 molar concentrations for everything. That's what, remember, this little thing right here means, standard conditions. We do the anode minus the cathode. So we get 0.34 plus 0.76 gives us 1.1 volts. The higher that number is, all right, the more positive the value for the reduction, the greater the tendency for reduction to occur. So the stronger the oxidizers are going to have, or the stronger the oxidizer is, the greater the reduction potential. You can see those there on the left. Those are our stronger oxidizing agents. And some of our more common oxidizing agents that we end up using are like the halogens, oxygen, all of the, or well, not all, many of the oxyanions, things like MnO4 minus, which we use at the beginning, dichromate, which is Cr2O7, nitrates are good oxidizing agents. And the opposite is going to be true for your reduction potentials, right? So like lithium is the easiest thing to oxidize, so it is the strongest reducing agent. Common reducing agents are like H2, like hydrogen gas, your alkali metals, your alkaline earth metals, zinc, and iron, right? So those are all really good reducing agents. Iron, zinc ions. So can we tie all this into stuff that we've looked at earlier in the year? Oh, absolutely. We can tie reduction and redox into free energy. So a spontaneous redox reaction is always going to have a positive cell potential. The more positive the EMF is, then the greater the spontaneity, right? The more likely it is to occur. Well, we know that this is true for not only redox reaction, or not only voltaic cells, but also for all redox reactions. So we can drop the cell at the beginning of this E formula right here, and instead of having anodes and cathodes, just look at it in terms of reduction and oxidation. Now, we know that Gibbs free energy, all right, is the measure of spontaneity. And so a positive EMF is going to correspond with a negative delta G. And this is the equation that relates those two ideas. F here is the Faraday constant, which is 96,485 coulombs per mole, which is often written joules per VMOL, volt moles. All right, that's the same way we can write that because we know a coulomb is a joule per volt. And another way you might want to, and I think I was going to say you might want to memorize Faraday's constant, but it is on your AP constant sheet, so you don't need to memorize it. N right here is the positive. It has to be a positive number, and it's an integer. All right, positive integer, and it is going to represent the number of electrons transferred in the reaction. All right, and E, that is your EMF. So it's the thing that we calculate when we do the reduction potential of the reduction side minus the reduction potential of the oxidation side. Okay? Well, how do we put all that together with stuff we already know? Well, we know that delta G is equal to negative RT ln of K. So we can now relate the electropotential capabilities of a cell to the equilibrium constant K, which I'm sure you are so happy to hear. And we can even do that under standard conditions because we have, an E and we have an E standard. So we can put those two things together. Now, under standard conditions, I'm going to do a problem for you guys in another video where we calculate delta G and K and E all in one big math problem. So I'll get you an example video posted here after this one. But this stuff all applies under standard conditions, right? Because when we see K, we're talking about equilibrium constants. We see that little prime symbol right here, right there, right there, or right there. All of those things have to do with standard conditions. But what happens if we're trying to do something, we're trying to find a value under non-standard conditions? Well, we use what's called the Nernst equation. And so the Nernst equation takes our G value, our Gibbs free energy value, and its relationship to standard Gibbs free energy, which we see there in the first one, and it substitutes that with the negative NFE equation that we just looked at. When you divide both sides out, you get the Nernst equation, which is E equals E standard, E prime, minus RT over NF times the ln of Q. Now, we can solve this and convert the natural log to a logarithm, base 10 logarithm, using this 2.303 factor. And under standard temperature, this actually is calculated a little bit ago. Yeah, here we go. You get at 298 Kelvin, that equals 0.0592 right here. Yep, there it is right there, 0.0592. So this is our Nernst equation at 298K. Now, the Nernst equation is something that we will look at in that second video in the problem where I actually solve one of those. But the Nernst equation is what we use to find E when we don't have standard conditions, right? We just need to know E from our standard cell, and then we can calculate whatever we need. Now, Q, all right, is K at any time other than equilibrium. Q is going to take into account the concentrations of reactants and products. Like all of that is going to be the same as it was when we did equilibrium. So again, when we get to the math sample problem video, you'll see some of those in action. For now, just make sure you know what the Nernst equation is and when you use it. Now, the last thing we're going to look at in this first video is the concentration cell. I'm not going to spend a lot of time on it because, quite frankly, the AP test doesn't spend a tremendous amount of time on electrochemistry. However, you should be aware of the fact that if you have a voltaic cell that's set up with the same species on both the anode and the cathode side, if you vary the concentrations in those two sides, then you can actually create a voltaic cell. We see this in biochemistry primarily. We see it in pH meters. We see it in things that are like bioelectricity, like the eel here, things that are living that can conduct electricity. We see it in the pacemaking cells that run your heart. It's a pretty common thing in biochemistry. Basically, by varying the concentrations between the two cells, you get the flow of electrons. Some things that we want to know here. Number one, reduction is going to occur in the cell that has higher concentration. Number two, you can use the Nernst equation to calculate E here. And when you do that, Q, instead of reactants over products, will be the concentration of the dilute side over the concentration of the concentrated side. Okay? Again, not something that we see tremendously in chemistry other than in biochemistry and if you're trying to build a pH meter, right? So I wanted to at least talk about that. It is in your book. You can read about it. There's a pretty cool inset in there about, I think it's your heart cells. So, all right. That's the end of the first video on electrochem. I am going to post some sample problems as a separate video, and then we'll also talk about batteries in the third video. So I'll see you guys in the next video. If you have any questions, let me know.